All right, let's go on a journey. We're going to start with a messy pile of data and end up with a real-world prediction. This is the data analyst journey, and you'll see it's a lot less about being a math genius and a lot more about being a detective.
So when you hear data science, what do you picture? Is it just endless lines of code, super advanced math, algorithms you can't even pronounce? I mean, that's the common idea, but it's missing the most important piece of the entire puzzle.
Because at its heart, a great data analyst isn't just a programmer. They're an investigator. They're driven by plain old curiosity and common sense. And they are constantly asking one simple, powerful question. Why? That question comes way before they ever worry about the how or the what. So, where does any good investigation start? Well, with the evidence, right? And in our world, that means you've got to get to know your data. I mean, really get to know it.
This first step has a name: exploratory data analysis, or just EDA. Think of it as giving your data set its first health checkup. Before you can build anything with it, you need to understand it from the inside out. And you know what your most important tool is for this? It's not some complicated algorithm. It's your own common sense.
So, what kinds of clues are we looking for here? We're basically on the hunt for anything weird, anything unexpected. Are there drivers that just don't make sense? Things we thought were important, but turns out they're not? We're also looking for odd patterns, or even just plain old typos and weirdness in how the data was entered. And you know what? A lot of the time, this whole investigation kicks off with one single, super simple command: data.describe it. This just gives you a quick snapshot, a summary of your data's vital signs. It's like its very first health chart, and it can tell you so much about the story that's hiding in all those numbers.
Okay, so once we've had our first look, it's time to roll up our sleeves and get our hands dirty. See, raw data is almost never ready to be used as is. We have to clean it, shape it, and get it all prepped, kind of like a chef preparing ingredients before they even think about cooking.
Now, this might look a little complicated, but it's showing a huge, really common problem. Just imagine you're comparing two things. One is, say, a rating from 1 to 3, and the other is a salary that's in the thousands of dollars. Well, when you try to analyze them together, that giant salary number is just going to completely drown out the tiny rating scale. As you can see here, the big number can end up influencing the result by over 99%, making that smaller but maybe really important variable pretty much invisible.
But the good news is there's a pretty straightforward fix for this. It's a technique called standardization. All it does is rescale all our variables so they're playing on a level field. This just makes sure that a variable's importance comes from the actual information it has, not just from how big its numbers are.
But our prep work isn't quite done. What do you do about all the empty cells in your data? Well, that's where something called imputation comes in. It's a smart way of filling in those missing puzzle pieces. And what about data that isn't a number, like the name of a city? For that, we use a trick called one-hot encoding, which is basically just a way to translate words into a simple code of ones and zeros that our computer model can actually work with.
Okay, so our data's clean, it's properly scaled, we're good to go, right? Well, what happens when some of your data points are a little too similar? What if they're basically just telling the exact same story, but using different words?
Yeah, that problem has a name: multicollinearity. It's what happens when two or more of your variables are so alike that they create this kind of echo in your data, and it can really mess up your results. To find that echo, we use a special tool called the variance inflation factor, or VIF. Just think of it as a score that tells us how much one variable's story is already being told by all the others.
All right, the data is prepped. The ingredients are ready. Now we get to the really exciting part, actually building the model that's going to make a prediction. It's time to build our crystal ball. To understand one of the most intuitive models out there, all you really need to remember is this one simple idea. It's the entire concept behind an algorithm called k-nearest neighbors. It's elegant, it's simple, and it is surprisingly powerful. So here's how that simple idea actually works. The k-nearest neighbors algorithm, or KNN, has 4 really easy steps. First, you start with your data. Second, you figure out how you're going to measure closeness. Third, you pick a number for k, that's how many neighbors you're going to ask for an opinion. And finally, to make a prediction for a new piece of data, you just find its k closest neighbors and let them vote. It's that simple. Majority rules. So we did it. We built our model, it's making predictions, but are those predictions any good? This is where the journey gets really critical. Now we have to be the judge and jury for our own creation. How do we actually measure success?
Now, your first instinct, and everybody's first instinct, is probably to just look at accuracy.
If a model is 99% accurate, it must be awesome, right? Well, not so fast. In a lot of real-world situations, a high accuracy score can be a really dangerous lie, especially if your data is unbalanced. It can hide huge, costly problems.
So we need better tools. Let's look at two of the most important ones, precision and recall. Precision asks this: of all the times my model predicted yes, how often was it actually right? This is super important when being wrong is expensive. Think about a spam filter that deletes an important email. That's a false positive, and it's costly. Recall, on the other hand, asks, of all the yes cases that were actually out there, how many did my model manage to find? This is what you care about when missing a case is the real disaster, like a model failing to flag a great sales lead.
But what if you have a few different models to compare? That's where a tool like this ROC curve comes in. Now don't worry about all the details on the left, just focus on the big idea here. This chart lets us see the trade-off between finding all the good stuff and accidentally raising false alarms. The best model is always the one that gets closest to that top left corner. That's the sweet spot. It means you're finding most of what you're looking for without crying wolf all the time.
So when we look at a chart like this one, which just sums up that ROC analysis, the choice becomes pretty clear. Yeah, models M1 and M3 might be okay, but model M2 is the one that really nails that perfect balance. It's the one we'd pick to move forward with.
And that brings us to the final part of our journey, at least for now. Because the thing about data science is the journey never really truly ends. It's always a cycle of building, testing, learning, and making things better.
And this leads us to maybe the most important takeaway of all. We are not chasing perfection. A model that's 100% accurate on old data is often totally useless in the real world. The real goal, the only goal, is to build a model that's useful, one that can actually be put to work and deliver real value.
And to really hammer home why we have to always ask why, let's finish with one last kind of mind-bending idea: Simpson's paradox. This is what happens when a trend looks like it's going one way, but when you look closer and split the data up, it completely flips. For instance, a new drug might look like it does nothing at all. But then when you split the patients into mild cases and severe cases, you suddenly see it's highly effective for both groups. It's the ultimate reminder that a hidden variable, like severity, can be secretly twisting your entire dataset. And that's the question I want to leave you with. As you go about your day, looking at headlines or reports, just remember this analyst's journey. Always ask why. What hidden factors might be shaping the numbers and the data you see? The investigation never really stops. Thanks for joining me on this one.